So this PSCAD example compares the detailed, switching model with the average model for the 50% voltage sag case with the strong grid. So look at the detailed model first. The first thing we'll point out is that the time step is 10 microseconds. We go down to the ComTrade recorder. The file is DM right there. Most of the case doesn't change between these two variants, but if we look, I'm going to dig into the solar farm. This is the way the model was originally developed. You can see a bridge of 6 IGBTs here, and the PV panels are to the right. The filter and the inverter transformers are up to the left. Let me scroll down and we'll see that the firing pulses are generated. This block number 4 here generates the phase voltage references. So what were MA, MB, and MC in the introductory video, they're called ref_A, _B, or _C. That is, right here. And then we go down to these firing pulse generators, and you need to read the PSCAD documentation for how those work, but basically you see a carrier signal being generated here, and then these 6 tall vertical blocks are generating the firing pulses for each of the the 6 switches in the bridge up at the top. So let's come out, and I won't run it now, but what you would do is you just hit the the run button and run that simulation, and it should be good to go. I want to compare that to the average model version, which is Solar 3 AVM. And by the way, these are unzipped to the same directory we've been using, C:\temp\I2X. And if you unzip to a different place, then you adjust your paths accordingly when we come time to the post-processing. If you already had files in that directory, it should be safe to overwrite those. Don't worry about that. So here I've jumped into the Solar AVM model, the average model, and if I go back to the project, so the time step is 50 microseconds. On the recorder at the top, I set that to AVM is the file name. I'll show you that. But in the middle here, that bridge has been replaced with these average controlled sources. You can see part of the calculation of the DC current source there. But over to the right is the DC bus, and over to the left is the LC filter. Notice that the things being used in the equation are these ref_A, which were the modulation indices, and they're generated down below as they were before. So I'm going to scroll down and generate DQ, reference voltages. So part 4 is unchanged. Didn't change this at all. Okay. So I added some plots, and it's nice to add some plots if you're trying to figure out how a model works or debug something, or just learn for your own knowledge and extend maybe the model or develop your own new ones. But in the firing pulses, notice that the carrier source and all those firing pulse generators are grayed out. So that is one change. I just disabled that. One thing has to be kept in. The carrier frequency. So I'm not actually using it, but it's 60 times 60 or 3600 hertz. Why do I need that? I'm not actually using it to generate the carrier pulses, but it's actually used in this block here. It's kind of an auto sizing feature to design the filter components, and it does a pretty good job because you're going to see that there aren't that many harmonics produced. But this FCR is a carrier. So if I were to change a carrier frequency, I'm going to get different PWM modulations and different harmonics, but the filter design is going to be updated accordingly. So that is a nice feature in the design. It comes with this model. Okay, I should be able to go up, and so the power plant controller didn't change between these two, but this showed you the time step. We're running for 10 10 seconds. And the file name, you don't want to overwrite the file, but it is not DM, but it's AVM. And basically the setup doesn't really change. You may change the sampling rate, the sample ratio. One thing you may have to do is change the config file that's produced when we do the detailed model. I'm going to double check that, and I'll put a note in the comments below this video if you need to make a manual edit to that file. So here we have run both simulations, the detailed model and the average model, and I've opened cplot 3 notebook in Jupyter. Comes up in the web browser just like we've been doing before. I'm going to run these cells. So this is loading the ComTrade support library, the channel loading function. I'm going to read the MATLAB package and some support functions that are going to make those plots. And I'm going to, we're doing PSCAD now. So if you extracted to temp/I2X, then you wouldn't need to change this. If you extracted it some other place, edit that to match. I'm going to click run that. So we should read the ComTrade data files. And it's still running, and looks like a success. We got the files from, the data from 2 files loaded. I'm going to skip over the EMTP results, and then I'm going to run, let's just show the comparison plot. You can click either one of these if you want. This particular example, because the filter design is so good, doesn't have a lot of harmonic content. So what we're doing is we're comparing the detailed model or the switching model in blue and then the average model in orange. And from a system dynamics perspective, these are pretty close. There's a little bit of difference in the reactive power response between the 2 models, but the frequency, the real power, the voltage, they all look pretty close. So from a system dynamics perspective, the average model is probably good enough, and you could run at a 5 times longer time step. But I want to look at the harmonics. We're going to pick the phase A grid current in a window of, I think 50 or 100 milliseconds. I think 100 milliseconds. In Python, we have the scipy.fft package, and we're importing a couple of functions, FFT and the FFT frequency. One nice thing about the modern FFTs is that the number of points doesn't have to be a power of 2. So it'll figure out what it does is it does a prime number factorization of your number of points. So if you have exactly 1,000 points, you can do an FFT on 1,000 points, not the 1024. So what that means is when you're doing a simulation of 60 Hertz phenomena, you don't have to do an FFT windowing. It may be a good idea anyway, but I didn't do it here because it's not necessary. So these functions are going to just define some service functions. We're going to, this grid current window is going to take a slice between T1 and T2 of my time and my channel that I want to do the FFT analysis on. This get spectrum is going to do the FFT, and it is going to, so the function that does the FFT is this FFT-OY, and then FFT frequencies are going to kind of fold the spectrum in half and take the frequencies that I'm interested in Hertz, and then I want the magnitude. So the FFT comes back with real and imaginary parts. I could convert that to magnitude and angle, but we're normally interested in the magnitude only. So that's what this np.abs, taking the absolute value and kind of folding it in half and getting that. I want to be able to plot the magnitude. Then I'm going to do some numerical outputs. Pick out the peak of the magnitude spectrum. That's my highest component, and we can get the RMS of that highest component. So this is going to be 60 Hertz. We want the total RMS considering all of the components. I'm taking the sum of the squares, so the magnitude squared here. Take the sum of that, take the mean of that, divide by 2. So I'm getting the RMS magnitude, not the peak magnitude, and then take the square root of that. So in numerical outputs, I can get these 4 different quantity measures, and this is a function that's going to plot the magnitude of the current, and also the frequency spectrum. So this does everything at once. I'm going to run that cell. It's going to take a little while to import that SciPy package, but did. All right. So this is a very clean waveform. Notice the switching model is 10,000 points at the 10 microsecond time step. The average model is 2,000 at 50 microseconds. The fundamental peak, the fundamental RMS, the total RMS, they're all pretty close. The harmonic distortion of the switching model is less than 1%, which is good. And the average model is even less. Visually, you can't really tell on this scale. And this is the magnitude plot on a semi-log scale. I wanted to show you one last thing before we conclude this example. When you set the ComTrade recorder for the detailed switching model, you want a 100 kilohertz sample rate to match the 10 microsecond time step. There may be an issue when it writes out the ComTrade config file. So if that's the case, if you encountered an error in what I just showed, trying to read that ComTrade data into the Jupyter Notebook, find your dm.cfg file. It's right here. So I'm using the Intel Fortran compiler. Your path may be slightly different, but you can notice in the Jupyter Notebook input cell where it's looking for this file. Look down here. Here's your channel definitions. You see 60 hertz is the system frequency. Some of these, one of these two numbers, it may have ampersands in it or hash signs. And if that's the case, just do a hand edit on the file. It's 100,000 samples per second, and then 600,000 total samples. If you encounter an error loading the data in the Jupyter Notebook, just check those two numbers.